Hey everyone, welcome into this lecture video on integration by parts. In this video, I'd like to compute a couple of examples. So in this example, we're asked to compute the antiderivative of t squared times e to the minus t dt. And what we would like to do is treat this, number one, if we know the answer, we can just write it down, right? But just by looking at this does not look like a function that we know the antiderivative of just by staring at it. So instead, what we need to do is try to approach this by integration by parts. And the reason we know that that's a good approach is because this looks like a product of two functions. But remember, the integration by parts formula is integral of u dv. So this is in our kind of reduced symbolic form. This is equal to u times v minus the integral of v du. And the whole idea here is that this d, this differential, which is like a derivative in some sense, moves from v over to u. And so when we make our choice of our u and our v, we want to make a choice that is going to benefit us, right, from moving the derivative from one function to the other one. So just ask yourself, if you were trying to do this problem and you wanted to try to make it simpler, like simplify this problem, right, would it help to take the derivative of t squared more, or would it help to take the derivative of e to the minus t? So before we do anything else, let's just write down those derivatives. The derivative with respect to t of t squared is equal to 2t, okay? The derivative with respect to t of e to the minus t is minus e to the minus t. And notice that in terms of an integral and kind of like becoming nicer in some sense, the function t squared, after taking the derivative, we reduced the power on t. And we made it better in some sense, at least in that sense, right, that the power is nicer. This function e to the minus t, the derivative multiplied it by a minus sign, but it did not change really the function at all. E to the minus t is still there. So this tells us that when we apply our integration by parts formula here, we want to do it in such a way that when the derivative moves, it moves onto t squared, right? So what that tells us then is that just by observation and comparing with the formula, this function should be our u, right? And once we've made a choice for our u, the rest of the equation has to be our differential dv. All right, let's apply the formula to this. If we say our u, I'll just write right here, if our u is t squared, then in our formula, we're going to need to know du. That's part of the formula over here, right? So if this is u, this is du. By the way, we already know u, right? U du. Well, the derivative we just said is 2t dt, right? That's the differential now. 2t is the derivative, 2t dt is the differential. And on the same hand, we have dv here, had to be e to the minus t dt. That's here. We need to integrate that to find v, right? If you integrate dv, you get v. And the integral or antiderivative of e to the minus t is also, in this case, minus e to the minus t. So there we go. We've got our v, we've got our u and our du. We can put this all together now, right? So by applying this integration by parts formula, we learn that the integral of t squared e to the minus t dt must be u times v, right? So t squared negative e to the minus t. So it's negative t squared e to the minus t, and then minus this, right? Minus this with an integral. So this becomes minus the integral of 2t, another minus right here becomes plus e to the minus t dt. So this minus and then this one from the formula, right, cancel out to give us this. All right, so let's write one more step here. We've got minus t squared e to the minus t plus that 2 can come out, right? So plus 2 integral t e to the minus t dt. And notice that we still have an integral here, right? But it is better. We've reduced the power of t by a power of 1. And so now we just have to repeat the whole process. And we've already talked it through, and it's going to be the same situation, right? Because we still have an e to the minus t. So that t is going to be our u, and this whole e to the minus t dt will be our dv. So I'll write over here this time. If our u is t, then our du is just dt. That's good, right? It's getting better every time, and we're getting less powers of t as we move along. Our dv is going to be e to the minus t dt again, and we already know then that v is going to be minus e to the minus t. And then we apply our integration by parts, which says u times v minus the integral, right? Minus the integral as you go across this way. All right, so let's see what's going to happen here. This becomes, write down everything we have. You don't want to lose what we have. Negative t squared e to the minus t plus 2 times, in parentheses, u times v. So that's a minus t e to the minus t minus this direction. So that becomes a plus. Minus minus is plus. Integral e to the minus t dt. And then we still have to integrate one more time, right? But this one we know exactly what the answer is. So this is now minus t squared e to the minus t minus 2t e to the minus t minus 2, that 2's got to go everywhere, right? Integral e to the minus t dt. And the integral of e to the minus t, oh, this is plus, sorry. That's a plus sign. So this integral is going to be a minus, so I was getting ahead of myself. And our final answer here is this is negative t squared e to the minus t minus 2t e to the minus t minus 2 e to the minus t plus c. And that's the integral of t squared e to the minus t dt, the antiderivative, I should say, by applying the integration by parts formula. Okay, I have one more example. This one's similar, but just different enough. This one is cosine t e to the 2t. And just based on our conversation from the last example, the last problem, we noticed that whenever it's an e to a power, that's not going to be a good candidate for choosing for u, right? Because as we saw back here, the goal was to get the derivative when it hits u to change u somehow, right? To change u. And any power of e to the minus t in this case, or e to the 2t in our current situation, all it's going to do is multiply by a constant, and it's going to leave the function the same, right? So that's not what we want. This is good. This is going to be our dv. Whenever we have an exponential, it's going to be our dv. Well, that just leaves this to be our u, right? Cosine to be our u. So let's see what happens. If u is equal to cosine of t, then du has to be what? The derivative of cosine is minus sine of t. So that's a differential, dt. And then our differential dv is e to the 2t dt this time, which means that v is the antiderivative, so it's 1/2 e to the 2t. And now we apply integration by parts again. It always goes diagonal this way, multiply those together, subtract the integral this way. From right to left is subtraction, right? So left to right is addition. You're going to multiply them together. Left to right, subtraction. Yeah. So what's it going to give us? This one's going to become, if we just write this out, 1/2 e to the 2t. So let me 1/2 e to the 2t cosine of t. Keep it in the order it was given to us in, right? Minus a negative, so there's another negative here, so this becomes plus 1/2 integral e to the 2t sine of t, but again, I just said I was going to keep it in the same order. So let's write this as sine of t times e to the 2t dt. And let's remember that this is, of course, equal to integral cosine t e to the 2t dt. Now we need to apply integration by parts on this one again. So this is the second example, and in both examples we've had to apply integration by parts twice. All right. Sometimes you get the job done just by doing it once. Sometimes, though, it does take 2 times. So we've got the same scenario, right, where there's an exponential. So that's going to be our dv. And let's write out all the work that's going to happen here. So this one's going to be u equals sine of t. Du is then equal to cosine of t dt. And then our dv, of course, is equal to e to the 2t dt. And v is the antiderivative, so 1/2 e to the 2t. And then we apply the algorithm. So multiply, subtract the integral of these ones, right? Let's see what we get. I'm going to remind us that this is the integral of cosine of t e to the 2t dt. On the right-hand side, we have 1/2 e to the 2t cosine of t, plus, then we have this 1/2 hanging around, right? But we're going to have another 1/2. So this becomes 1/4, right? 1/4 e to the 2t sine of t. And then we got to subtract this off. It's still got the 1/2 times 1/2. So this becomes minus 1/4. And then the integral of e to the 2t cosine of t dt. And at this point, you're probably feeling like we are stuck in a loop, and you're not wrong, right? This feels like a loop because what's happened? We've done integration by parts twice, and we've basically undone everything that we tried to do, right? But we didn't exactly, because over here we have negative 1/4 copies of what we started with, right? So if you were to call this I for integral, then this over here is another copy of I, right? And just by treating that like a variable, you can think in your mind, okay, I've got one I over here, I've got negative quarter i's over here, I can add this over, and on the right-hand side, I now have 5/4 of my integral I, right? So I'm going to rewrite what the integral was, but 5/4 the integral cosine t e to the 2t. Now it equals all this, right? So it equals 1/2 e to the 2t cosine of t plus 1/4 e to the 2t sine of t. And we have a couple more things left to do, but we're basically done because now we have a formula for a function, right, whose antiderivative, whose integral is equal to this, kind of, right? It's not exactly, because we've got this factor of 5/4 here. And then, of course, we also always need, when we find an antiderivative, a plus c. So let's do this in steps. We are going to multiply the entire equation by 4/5, right? Distribute that all the way through, and then we'll have one of these on the left. That's what we wanted, right? That was our goal in the first place. Cosine t e to the 2t dt. When we multiply this through, we end up with 2/5 e to the 2t cosine of t plus 1/5 e to the 2t sine of t. And now we have to make sure that we add in our plus c. The plus c has to be there at the end. All right, and so this is kind of, you could refer to this as like an algebraic swindle. It's not really a swindle at all. We just applied integration by parts 2 times. We found out that after doing it twice, we got caught in a cycle, but we were able to get out of the cycle by noticing that we could just add this whole term to the other side, combine like terms, and then do a little bit of algebra or arithmetic, right? And so we were able to solve this integral by a careful and kind of clever application of integration by parts.